Okay, in this video we're going to talk about the properties of amines. So the nitrogen atom in amines is typically sp3 hybridized. So remember, when nitrogen is neutral, it has 3 bonds and 1 lone pair. So typically that lone pair resides in an sp3 orbital. Of course, if there was a double bond to the nitrogen, then it would be sp2 hybridized, or if this lone pair is participating in resonance, then the nitrogen is going to be sp2 hybridized. I'm not going to spend a whole lot of time talking about this, but I think it's worth mentioning. The nitrogen in amines can be chiral. If the nitrogen is connected to 3 different alkyl groups, then that nitrogen is in fact chiral, because the lone pair counts as a 4th group. Now, the reason I'm not going to talk a lot about this is because amines are generally not optically active. So these are 2 different configurations of this chiral amine, because we have 3 different R groups and the lone pair. But the barrier to inversion, and we call this a pyramidal conversion, so we go through this transition state, that barrier is only about 25 kilojoules per mole, which is not very high. So at room temperature, the amines are able to flip back and forth between the 2 configurations, and so other than at really low temperatures, we tend to have a racemic mixture. We have both of the configurations present. And so we often don't talk a lot about chirality in amines, but if you're doing something at really low temperatures, that might become more relevant. Now, like most of the other functional groups that we've looked at these last 2 semesters, the amines introduce some polarity into the organic molecules. The nitrogen is considerably more electronegative than the carbon, and so there's a pretty strong partial negative charge on the nitrogen most of the time when we have these amines. Furthermore, in the case of primary and secondary amines, the hydrogens connected to the nitrogen are able to participate in hydrogen bonding. And so this has some significant impact on the properties of amines. Amines with fewer than about 5 carbon atoms are typically soluble in water. When we get too big, all those carbon atoms in the big nonpolar part of the molecule will swamp out the polar part and it won't be soluble in water anymore, but at least the small amines are typically fairly soluble in water. These polarity of the amines and the hydrogen bonding also plays a role in the boiling points. You can see that amines have higher boiling points than similarly sized alkanes, but not quite as high as water, the oxygen being more electronegative than the nitrogen. And you can also see that the primary and secondary amines tend to have significantly higher boiling points than the tertiary amines, because with no hydrogens directly connected to that nitrogen, it doesn't have any hydrogens that can participate in hydrogen bonding. It can be a hydrogen bond acceptor, but it doesn't have a hydrogen itself that can participate in hydrogen bonding. Another interesting thing to note about amines is that particularly the small ones often have unpleasant odors. If you've smelled ammonia, that is a pretty powerful odor that I think most people don't find particularly pleasant. If you're not familiar with it, if you've ever smelled Windex, the smell that Windex has is largely from the ammonia that's in it. But you can see these 2 small amines in particular, you can probably guess based on their names, putrescine and cadaverine are probably not 2 pleasantly smelling compounds. Maybe the most important property of amines that you want to remember is their basicity. So amines are significantly stronger bases than alcohols and ethers. And so the lone pair on the nitrogen is what makes them particularly strong bases, and they are readily protonated by both strong and weak acids. So carboxylic acids will readily protonate the amine to give us an ammonium ion. And so, kind of in organic chemistry, carboxylic acids are our typical weak acids, and amines are our typical weak bases. Now, we talked about solubility earlier, but I think it's important to come back and talk about it now that we've mentioned the ammonium ions. So in general, amines with more than about 5 carbon atoms are either not soluble or only slightly soluble in water. However, in the presence of aqueous acid, where I can protonate the amine to make it an ammonium ion, so I go from the neutral amine to the positively charged ammonium ion, this greatly enhances its solubility, because rather than just being polar and then trying to counteract this big nonpolar piece, we have a full-on positive charge. And so the ammonium ions are typically much more soluble in water than the neutral amines. And we can take advantage of this in extracting amines from other organic impurities, or if they're the impurity, we can extract them by making the ammonium ion, and then this will be soluble in the aqueous layer as opposed to the organic layer. And in fact, if you took Chem 2211 at GGC, you did this in the extraction lab, where you had to separate a couple different compounds by doing liquid-liquid extraction and by changing the pH by either adding hydrochloric acid or sodium hydroxide to adjust the pH, and then changing whether the carboxylic acids and the amines were charged or the neutral compounds. Now, there are a number of factors that can influence the basicity of amines, and one of those is resonance. In particular, if we look at aryl amines, so we have an amine coming off of a benzene ring, because we can draw resonance structures where that lone pair is delocalized around the benzene ring, it is less available to accept a proton. Or if we think about resonance being a stabilizing factor, when we stabilize that lone pair, it's not as reactive, and so it's not going to be as strong a base as an amine not coming off of a benzene ring. Now, back when we were talking about the acidity of carboxylic acids, we looked at the effect of electron withdrawing and electron donating groups, and so we can do the same thing when thinking about the basicity of the amines. And so what we're showing on this slide is we have just aniline as sort of our control, and then we've added an electron donating group and an electron withdrawing group. And so you can see what happens to the pKa of the conjugate acid. So we're sort of using this as our reference. When I put on an electron donating group, that increased the pKa of the conjugate acid. That means this is a weaker conjugate acid, but that means that this is a stronger conjugate base. And so, right, that's donating electron density, so we're going to have more of a negative, partial negative charge on this lone pair, and so that's going to make it a better proton acceptor. On the other hand, when I put on an electron withdrawing group, that significantly lowers the pKa of the conjugate acid. That means, right, a stronger conjugate acid is going to make a weaker conjugate base, right, as we're withdrawing electron density from, when we have electron withdrawing group, right, that's removing electron density from here, and so less electron density is going to be a less good proton acceptor, and it's going to be a weaker base. Okay, and one final note on this video on the properties of amines is comparing the basicity of amides to amines. So as we've talked about, amines are generally pretty good bases. Amides are not particularly good bases. The reason being, in an amide, there's significant contribution from this resonance structure, and so the lone pair is delocalized between the oxygen and the nitrogen, and so it's really not available to act as a proton acceptor. And so while amines are good bases, amides tend not to be.